I chose this one rather than A or C is we know the Robinson annulation makes 6-membered rings, so there's no ambiguity about the fact that this is the ring that came from the Robinson annulation. So if we want to work backwards, we know that the last step of the aldol condensation makes the alpha beta unsaturated carbonyl. And so we know that that came from a beta hydroxy ketone. So we can work backwards by putting that hydroxyl group here. To make the beta hydroxy ketone. So that was the immediate precursor. And then we know that the aldol condensation is a reaction of an enolate onto a carbonyl compound. So that bond, right, and thus this bond, is the one that's formed from the aldol condensation. So we can further work backwards by breaking that bond. And putting the carbonyl on one side and the CH3 on the other side. You could actually have gone directly from here to there by recognizing that when you break this double bond, you add the oxygen to one side of it, and you add 2 hydrogens to the other side. So we're adding the oxygen to this side, and we're adding the 2 hydrogens to the alpha carbon, always adding the oxygen at the beta position. So this is the 1,5-diketone that resulted from the Michael addition, and the other bond that's going to be formed is that one, because it's from the enolate here. So we can work backwards some more. You get this nice symmetrical molecule, and then the other component was, in fact, MDK. So another one, reason I chose this one is MDK is kind of the classic Robinson annulation. And here we have 2-methyl 1,3-cyclopentane dione. And that's nice because it's symmetrical, so we don't have to worry about which of these 2 carbonyls is going to act as the acceptor in the aldol condensation, because those 2 carbonyls are identical. And so that makes it a little less ambiguous. So that's the retrosynthesis. And now what we want to do is work forwards from these 2 components to come up with the mechanism for reaction.
Is that is MBK the only way you can do it?
No.
Okay.
Any alpha beta unsaturated carbonyl would work. So this doesn't have to be a methyl group, it could be ethyl. You could have substitution at this position or this position.
I had substitution at the bottom position, and
Yeah.
it didn't have the CH3 on the other one, so when it connected, it added a CH3.
Yeah, but it wouldn't have added it to there.
I think it would have.
Because if the CH3 was here, I'll show you that in a minute. The CH3 would have ended up on the carbon in the 6-membered ring. Right? Because this carbon is going to become part of the 6-membered ring.
Okay.
So that methyl group had to be on the precursor. So, right, if you were working backwards, so you are always taking 4 carbons from the alpha beta unsaturated carbonyl and 2 carbons from the other compound. So if you work backwards like this, these 4 carbons are the ones that come from MDK. So if you attach your methyl group here, your product would have been that instead. The methyl group on that carbon
Okay.
that came from MDK. Which is close, but not exactly the same compound. So the first step is going to be to take the hydrogen off here and make enolate. and it doesn't matter which oxygen you take it to. And that's a really stable enolate, because not only do you have this resonance structure, but you also have two other resonance structures in this case, rather than just one other resonance structure, because you can push it to the other oxygen as well. This is what it's going to react like. That these two resonance structures, which are equivalent, are the more stable ones. In fact, because of two resonance structures, because it's in between two carbonyls, the pKa of this hydrogen is actually approximately 9 rather than approximately 22. So there's no doubt that we're taking this hydrogen off and not one of the 4 hydrogens from the CH2 group, because it's more than 10 orders of magnitude more acidic. So we don't have to worry about more than one possible enolate ion. The second step is going to be the conjugate addition. So we're going to take this reforming carbonyl and push that pair of electrons over. So lots of arrows in that second step. That forms one of the new carbon-carbon bonds. So that's the new sigma bond that's formed as part of the Michael addition, and then we're simply going to protonate this enolate. Out, which one of those is coming off too. So that's our 1,5-diketone, that's the product of the Michael addition. Say 1,5-dicarbonyl because it doesn't have to be a diketone. It could have been a ketoaldehyde if one side had been an aldehyde. So we now have 3 different types of alpha hydrogen, not 4 in this case, because there's no alpha hydrogen here anymore, so there's only 3 different enolates that could form from this material. One of them is this one. One of them is the one we actually need in order to form the 6' ring. Result of taking off one of the hydrogens from the double group. And then we could, of course, take one of these hydrogens off. There are 4 equivalent hydrogens with 2 equivalent carbonyl groups. So another possible enolate that could form would have been this one. explain later in part 3 why that one isn't likely to give a stable product. The next step of the Robinson annulation is to form the new carbon-carbon bond here from this enolate. So this is part of that nucleophilic acyl addition. So we're going to be making this bond here. Starting over there, there's obviously some bond. And then we're going to coordinate that to generate beta hydroxyketone. Coordinate that alkoxide ion. And that's the end of the aldol addition. And you'll notice that steps 5 and 6 are nucleophilic acyl addition. We've added the nucleophile to the carbonyl carbon, and then we've added the proton to the carbonyl oxygen from that carbonyl group. Right, so step 4 is enolate formation, and then steps 5 and 6, the second 2 steps of the aldol condensation, are the nucleophilic acyl addition. Like almost all of the reactions in chapter 17 and 18 that involve the nucleophilic acyl addition at some point. We now need to eliminate. So we're going to take off one of these alpha hydrogens. This is our third enolate formation. All 3 of these pieces of the Robinson annulation involve an initial enolate formation. It's the first step of the Michael addition. It's the first step of the aldol addition, and it's the first step of that elimination. Everything goes through the enolates. And then the final step is to reform the carbonyl and lose hydroxide ion, thus regenerating our catalysts. Make it unsaturated carbon. Those last 2 steps are an elimination, but not an E2 elimination because it's not concerted. It's stepwise enolate formation, followed by loss of hydroxide, regenerating the catalyst. So even if you were unable to come up with the fact that this reaction was starting with 2-methyl-1,3-cyclopentane diode and NDK, hopefully you were able to write out this series of 8 steps. It was 16 points, so logic suggested it was probably going to be 8 steps, and you knew that that was an annulation of 8 steps anyway. So I chose it so that it would be unambiguous which ring was the one that was being formed, and so that you had symmetry so you didn't have to worry about multiple enolates being formed. And you probably didn't know that that had a decay of 9, but obviously that was where you had to form the bond, so you would remove that one. So the question is, why don't we get multiple products for this? I've already answered the question as to why we only get one enolate from the 1,3-cyclopentane diode, because that hydrogen between the 2 carbonyls is much more acidic than the others, and that's because we get 3 resonance structures, 2 of which have a charge on oxygen. I've already answered the question, I guess, why we don't get the enolate on this carbon. There's no hydrogen on there to remove, so we can't form that one. The answer to why this enolate doesn't directly attack is because the product would be a 4-membered ring. So you'll notice that if instead of protonating that enolate, I have chosen to try to use that enolate to form the new carbon-carbon bond. Product would look like this. Which is fine, it's going to happen. And it's actually probably going to happen more often than step 5, because it's closer. The four-membered ring is more likely to collide kinetically. You can protonate this. There's no problem with protonating that. But then when you try to form the enolate and do the elimination, you'd be trying to put sp2 hybridized carbons into a four-membered ring. sp2 hybridized carbons in a four-membered ring introduces even more ring strain than you already had. So if you try to keep this reaction going, the product would look like this. And that's just very sad, putting two sp2 hybridized carbons. Not just one, right, but two. You have to put one in there when you form the enolate, but then in order to do the elimination, you're introducing a second sp2 hybridized carbon, which means you've got two carbons in that four-membered ring that really want bond angles of 120 and have to have bond angles of 90. It's going to suck, and the reaction's just going to keep going backwards, and you will eventually reach equilibrium. So that's the reason why that one doesn't happen. But then what about this other one? That's a perfectly legitimate enolate, and there are four carbons or four hydrogens that contribute to that because the two CH2 groups are identical. So there's even more chance of a collision happening than there is with forming the one from the three hydrogens on the methyl group. So what's wrong with the product that would result in this one? Anybody want to?
Oh yeah, it's the bridge. The bridge will have a double bond. Sorry, it's the bridge. The bridge head will have a double bond, and that can't happen.
I don't know if anybody can hear Isabel because she's on the wrong side of the microphone. But what she said was that the bridge, the resulting compound will be a bridge bicycle. So we could do it. And you could come in here, you could go around and attack that carbonyl group. There's nothing to really prevent that. And if I number these carbons so we can kind of make sense of it, looks like that. This is carbon 1. That's the carbonyl carbon. That's the CH2. And so there's nothing wrong with that. That's a perfectly reasonable substance. And then we can protate it. The problem comes when we try to take this hydrogen off to form the new enolate, because now you're putting an sp2 hydrocarbon on a bridge head position. And because of the configuration of that, if you were to make a model of that, you would find that these three groups, because they're all attached to the other side of the ring, are held in a tetrahedral rearrangement. So you can't really put a planar carbon in a bridgehead position without introducing a bunch of ring strain in all three of these other rings. Right? And it would have to stay sp hybridized in the product because you would be eliminating the hydroxyl group to make a really unstable bicyclic structure, which now has that double bond after bridgehead. That's just not going to be stable. So for the same reason that the 4-membered ring is no good, if it does actually happen, it's just going to go backwards, and you're going to get the single product. So we're forming the one product from the Robinson annulation for the same reason we did in the other one that I did in class, that the products of the Robinson annulation for all the other possible addition pathways are not going to be stable molecules. So I'm going to save this so there will be a separate video.